I have shared my screen. Can you see it?
Yeah, I can see it. My can see yours. Go ahead.
Okay. Thank you very much, Jen, for inviting me to be speaking here. My talk today is basically a high-level and brief introduction to the area called computer experiment, which is one of the areas I am working on. So my talk today is more about methodology. So I'm not going to show you any specific practical examples. It's more about the methods. If you are interested, well, I can, due to the time limitation, I can only briefly mention what kind of concepts and what kind of tools we are going to use. So if you have any questions or if you are interested in the details, please contact me through my email. I'm willing to answer any questions. Okay. So let me first talk about our view regarding computer experiments. Basically, computer experiments. Computer experiment, we mean computer simulation models. It could be static model or digital twin, which may be kind of dynamic. Basically, computer experiments refer to the experiments taking place on the computer simulation models. So each computer simulation model can be, from our point of view, is regarded as a black box function. So you have input and you put something to the computer model and the computer model will give you an output after it finishes its computation. So this procedure usually is deterministic and it can be stochastic, but most importantly, it is expensive to get one run. And our objective is not just run the computer model once, because usually we want to understand different things. For example, the input-output relationship is a function relationship, or we want to optimize the output. We want, for example, we want to find the best input setting, or we want to understand how the randomness or the uncertainty from the input side will lead to a random or uncertain output. So if that is the case, we cannot just go through the traditional way because that will cost a lot of computational time and resource. It's not possible in today's complex computer simulation. So our point of view is to consider a different approach by building a so-called surrogate model. So surrogate model basically is a kind of substitution to the original computer model, which is built based on data science technique. So when I say data science technique, the data actually is also coming from the computer model, which means that we select some representative input and we run this computer model. Because the number of the input is limited, we do not want a very large number of different input sites. So we can control the computational time, or we have a fixed budget thing. So after we run this computer model at those points, we get output, and we use this input and output as our data to build a model. So after we have this surrogate model, we can do prediction based on the surrogate model instead of running the computer model again, so which is can be much faster. Okay, so first, I like to start with some concepts from statistics because my background is statistics, and what I'm talking about today is a surrogate model based on a statistical model. Okay. So statistical model basically is a model which is random or stochastic in the sense that the model itself does not give a unique answer. So you can realize this model or sample from this model, you get data, and the data has its uncertainty. So that's the nature of statistical model. So while we are interested in statistics, is so-called the inverse problem, which is that suppose we have the data and we want to infer which model is the right model or most close model that can generate this data. So that's a statistical inference problem. And from Bayesian point of view, to kind of accomplish this goal, we can use the so-called Bayes theorem by putting together our prior information and the data. So once we have both of them, we can use the Bayesian theorem to derive the posterior of the data. Okay, so when it comes to Bayes statistics, there are two types of Bayes statistics. One is called parametric, in the sense that the number of parameters is finite. And in contrast, we can have the so-called non-parametric Bayes, which means that the unknown actually is not a finite dimensional object. Really, it's a function which lives in an infinite dimensional space. And the prior for a function should be a stochastic process. So that's why we want to introduce stochastic process to our model. Okay. So another simple explanation is that if you consider a parametric case, like if you roll a dice, you get a random number. So the prior to this random number is distribution, random distribution. If you consider a random function, that's a different thing. Basically, a random function is you can think that each realization of this random function is a deterministic function. It's just like when you roll a dice, each time you see a number. Right? So this number actually is a realization of this random variable. And if you realize a random function, each time you get a deterministic function. So that's why we can consider stochastic process as a prior for the deterministic function. And the model I'm currently, that's what I'm going to introduce in this talk is the so-called Gaussian process model. So this Gaussian process model depends on two parameters, the mean and the so-called covariance function. There are different choices of covariance functions, and I'm not going to go to the details today. And one thing I like to show you is that there are parameters in that Gaussian process covariance which allow you to create functions with totally different kind of smoothness or some other properties. Let's consider smoothness. For example, you can see that if you choose this smoothness parameter to be 0.5, you will see very rough functions. This is 1D case. If you increase this number, the function realization become more and more smooth. And this is the most smooth case. It's an infinite smooth case. That's one-dimensional example. We also have two-dimensional examples. Okay, you can see two-dimensional rough functions and two-dimensional smooth functions. So the GP actually can be defined in an arbitrary dimension. So I just show you some simple ones which we can visualize directly. Okay, so what we are interested in with GP is that GP can help us to do supervised learning. Actually, well, it can be used to do a lot of different things. But first, I'd like to show you about the supervised learning. So this is a regression model, and what GP actually can provide. Those are some math formula. I'm going to skip this part. So I just like to show you this simple plot, which illustrates the capability or what GP model can do. So the one of the major difference between GP model and other models is A GP model can give not only a point prediction given by the red curve, it can also give a confidence interval at each point. Okay, so shown by the green lines. So the interval between these two green curves indicates the predictive uncertainty or the confidence, 95% confidence interval for the predictive point. You can see that we assume that we have observed those square points. You can see that if you consider a point close to the square point, the uncertainty is small. If for any point which is far away from any of the observations, there is a larger uncertainty which faithfully capture the spatial or temporal correlation between the data. So that's kind of good thing for GP. I'm going to show you something that GP can be used to do besides surrogate modeling. One of them is calibration of computer models. So when you have a computer model and you want to use it to make a prediction for some reality, and usually when the computer code contains some parameters which determines certain physical properties. For example, in some cases could be permeability, conductivity. Those are physical constants or parameters in that system, which you may not have 100% kind of accurate knowledge about those, what the values should be in their models. And in that case, one thing we can do is to calibrate the model so that it can better reflect the physical reality. In that case, what we need is the computer input-output as well as the physical input-output. So if we also have some physical data that can help us to adjust the computer model. So in this model, actually, the method is introduced by Kennedy and O'Hagan. There are more work being done after this seminar paper, including some of my own work. But the basic idea is to use GP to fit each part of this model. And one important part is the so-called the discrepancy. So the idea here is that a computer simulation, no matter how accurate or how complex the model is, it cannot 100% recover the reality. This is because when you build the model, there must be some simplification or assumptions you make. So it is important to take this discrepancy term into consideration once you compare the computer model output with the physical output. So we use the Gaussian process to fit this one, and we put a prior distribution on this theta, so which is the parameter you want to make adjustments. So this becomes a Bayesian model. You can use any of the standard Bayesian statistic method to make inference for this one. Another method I like to mention is so-called Bayesian optimization, which is also kind of popular method nowadays in machine learning. So the goal of Bayesian optimization is to do global optimization based on a complex black box function. So think about if this F is your computer simulator, and if your goal is to find the input value which maximize your output levels, think about if this F is something of your engineering design or manufacturing process, and you want to maximize the performance of this process. And if the input space is not so small and the computer code is kind of expensive to evaluate, you may need this Bayesian optimization method. Okay, this is a global optimization, which means that we do not assume F to be a function like a convex or any specific structure. So the idea is to do a sequential sampling. So first you sample some points. This first step is just like to build a regular surrogate model. You sample some points and you run the computer code over those points, and you make inference and you build a surrogate model. But next, what we want to do is to decide which point we are going to run. So from this step, we are going to sample at the point in which we believe there is great likelihood to observe the maximum. So the general idea is that we determine the next point by optimize and so-called acquisition function. So it depends on which method you use. There are a bunch of methods, but all of them or most of them are based on the posterior of the GP. Okay, so that's the general step. So here you have to optimize another function called acquisition function. So we have to do another global optimization. But this global optimization is easier compared to your original one if your original F function is a really complex function to access. So the general idea here is we have to balance between exploration and the so-called exploitation. So the idea is that think about this function. If you have predictive mean as the red curve, from this mean, you may see that maybe the right-hand side is more likely to have the maximum value. However, the left-hand side, although on average is not that big, but the uncertainty is big. That means there is a greater potential on the left-hand side to also get a good value. So that's what we call exploitation versus exploration. So here you can see that this is why we need to have access to the uncertainty of the model. So this is basically why we have to use a stochastic model like GP, because if you use a point estimate, if it does not reflect the uncertainty, you cannot have a way to consider how you can explore this surface over just to do pure exploitation. Okay. So let me conclude my talk today. Basically, I mentioned some advantages of those models. It can enable uncertainty quantification. And another advantage actually is that GP can accommodate complex data structure because it falls in a general Bayesian framework. So if you have any prior information, you may also build that prior information into your model. So I know that I have to skip a lot of technical details. So if you are interested in those things, please feel free to send an email to me. Thank you very much.
Thank you, Ray. It's very, very technical presentation compared to others, but I think it's very helpful for most of us and who are doing numerical simulations and data-driven modeling. We have time for one quick question. Anyone, any questions from our audience? So just to let you know, GP is used a lot in the surrogate modeling and similar, modeling efforts just to reduce the computational cost in digital twins. And we do have 2 or 3 postdocs here at Tamitz. There are 3 of them are very good at the GP. So we are planning to offer, we are planning to offer a tech, called a tech talk or tutorial in the near future, probably sometime in this month. We'll make announcements very, very soon. And we'll have more or less a tutorial, like a discussion about GP methods. So,
that's great.
That's great.
Yeah.